All right.
Okay. Uh,
Go ahead.
welcome back. Welcome back to the after the coffee break and to the morning session. We will continue the last day of the Galileo Masterclass with an external speaker that is Ignacio Hernandez. He has been kind enough to accept our invitation to talk about the Galileo High Accuracy Service. Let me introduce Ignacio. Ignacio Fernandez has led the design and development of the Galileo High Accuracy and Authentication Services over the last years. He also chairs the EU, US Resilience and EU Authentication and High Accuracy Working Groups. He's an engineer from ICAI, Madrid, and has a PhD degree in electronic systems from Aalborg University. He currently is a visiting professor at Q11, where he teaches a graduate course on GNSS. He's the latest recipient of ION's Thurlow Hour. So, Ignacio, the floor is yours.
Thank you very much, Adria, and good morning, I guess, for the majority of you. Good afternoon, perhaps, for some of you. Thanks for your introduction, and thanks particularly for organizing this event. I have to say that it's a real pleasure, and I really mean it to be part of it. And I think it's that I say for the audience, it's a guarantee of success and knowledge. The fact that that UPC and GAGE group, I hope I said it right. Is it GAGE or Gage or I don't know. Well, in any case, it's a pleasure that you are contributing. I have to say, I joined before a little bit. I saw Jauma explaining some things, so I could see kind of the level of the course so far, which I think it's coming to an end, so it must be high. So I hope my presentation will not be too boring. But as I said, it's really a privilege to be around a renowned group as the UPC group, and in particular, Adria, we have worked together a little bit on the IONO future algorithm for hash. We will talk about it, so it's also a pleasure to be here with you. So without further ado, I'm going to proceed with my presentation. My presentation is on Galileo High Accuracy Service, which is one of the new services of Galileo we are putting in place. However, before starting with the high accuracy service per se, I thought it would be interesting to introduce some general sections or general concepts about, first of all, what is Galileo, then a general section on GNSS accuracy and the history of accuracy, how it has been improved over the last decades. Then talk a little bit about high accuracy. I know UPC are experts in high accuracy, but I hope a bit of repetition doesn't harm. I believe in repetition as a good, let's say, training strategy. And then finally, the last part of the presentation, but also the longest, will be on the Galileo hash or high accuracy service. Of course, I welcome any questions you may want to ask. If I can, I'll be very happy to answer. And I have a question to Adria, which is if I can ask questions to the audience, because depending on that, I can approach some slides in one way or another.
Yes, you can ask questions to the audience. No problem.
Okay. Okay, it's not that I will be doing that all the time, but perhaps at some point to make it more dynamic, I will do that. All right, so let's start with Galileo. Galileo, as you may know by now, is the European satellite navigation system, the European GPS or the European GNSS. Starting with the space segment, it consists of a constellation of MEO satellites, medium Earth orbit, between LEO, which is quite in fashion recently, and GEO, which has been already providing services for a long time. Our satellites are at an altitude of a bit more than 23,000 kilometers above the Earth's surface. And our constellation is designed as a Walker constellation with 24 nominal satellites in 3 orbital planes. So therefore 8 satellites nominally per orbital plane. The inclination of our orbits is 56 degrees, a little bit more than GPS, that is at 55, but very similar. Our orbits are a bit higher and also higher than GLONASS. And The phasing between planes is 15 degrees, which means that each satellite is equally spaced at 45 degrees within the circular orbit, and then the phasing between planes is so that they are also equally spaced. Um, this is a figure of one of our E06 satellites, just for you to have an idea. So some interesting things you can see here is this is the search and rescue antenna. This is the GNSS transmitting antenna with plenty of elements, including all our frequencies, E1, E5, and E6, as you may know already. The satellite weighs about 730 kilograms. Its power consumption is about 2000 watts, and the transmitted power per signal is about 30 watts. So what seems very surprising, even for people like me that have been working for 2 decades in satellite navigation, is how low the power of the signal is, taking into account that it's transmitted from more than 20,000 kilometers away, and how good GNSS works, even with a centimeter accuracy, as we will see later, with such a low power signals. You can see there the dimensions of the satellite. The satellites are dispensed in this fashion, in this configuration. This is the Fregat vehicle. Normally, we launch them in pairs of two, but we launched a few in groups of four with the Ariane 5 rocket. Normally, up to now, they were launched with a Soyuz rocket. Now, with the Russian crisis, there are some readjustments in the Galileo program, because there are no planned launches with Russian rockets anymore at the moment. And to conclude the explanation, the lifetime of the satellites is foreseen to be about 12 years. So if you compare two things that you may know, well, the weight is about a Formula One car. They are a bit heavier this season. I put Carlos Sainz Jr. I think that in Brazil there are very good drivers, Senna, Piquet, Piquet, Fittipaldi. So I don't know if there is some interest in Formula One in the audience. Anyway, the weight is about that of a Formula One, although satellites go much faster, we have to say. The power consumption is about a hair dryer. I had this presentation from before, and it was already in Portuguese. So for coincidence, I can uh, have it now in with an audience with this language. And then the transmitting power is like that of a small bulb before the LED bulb. So again, really amazing what we can do with such a low power. A very important element of the Galileo satellites and all GNSS satellites is the clock. So many people say that sat-nav satellites are just accurate clocks in orbit. The reason, as you may know already, is that we base our accuracy in time of arrival. Time of arrival depends on the accuracy of the transmitted uh, signal time, and therefore this has to be as accurate as possible in the long term and in the short term, and as stable as possible. So in each Galileo satellite, we have an ensemble of 4 clocks, which include two PHM or passive hydrogen maser clocks that you can see in this picture, and a pair of rubidium clocks, or rubidium atomic frequency standard RAFS clocks. The rubidiums, they have been used typically by GPS and all navigation systems, and the PHMs, we are the first ones to launch them. Uh, there you can see an approximation of the stability of the clocks, of the PHMs and the RAFs. You can see that the PHMs are more stable. On the other hand, as with every new technology, they are more prone to problems. And this is something we are experiencing now with Galileo. But their stability and performance is higher. I hope by now you are familiar with the term Allen deviation, which measures the clock stability for a certain period, which can be different depending on the period that you select. So clocks can have short-term stability or long-term stability. And this is measured by the Allen's deviation or Allen's variance, depending on how you refer to it. Important to say is that 5 nanoseconds equals 1.5 meter of ranging error. So we are really interested in having the clocks, in correcting the clocks as accurately as possible. This is our ground infrastructure. it's a pretty decent ground infrastructure for standard positioning services like the navigation ephemerides that we transmit in the navigation message of Galileo, in the typical one. As we will see later, it's not that developed for a PPP service, for a precise point positioning service. But this is what we have, and I will show later what we are doing with PPP. But what you can see is that there are stations worldwide. What we have more is monitoring stations, because we have to know, preferably with as most stations as possible, we have to see a satellite in every point on Earth. So satellites go like this, following their orbits. Then our 10-day revolution period as observed from a user on Earth. So we have to have stations everywhere. And then we have two control centers, the GCCs. And then we have a few stations for telemetry, tracking and control, TTC, and uplink stations. The uplink stations are the ones that are transmitting to the satellites the navigation message, and they are transmitting also the high accuracy corrections. If you want up-to-date information about Galileo, you can consult the GSC website, GNSS Service Center. There you can see up-to-date information on the constellation. So here you can see a list of the usable satellites as of yesterday, which means as of today as well. We have 23 usable satellites. So we are in initial service phase. So we are not fully operational, but we can say that we are providing already very good accuracy globally. So the service is, let's say, equivalent as being fully capable, the open service. We have, though, 5 satellites that are not usable or not available, which maybe for the users are generally the same. Maybe I will ask the first question just to ensure that the audience is awake. Do you know what you know probably these three lines which represent the 3 orbital planes? Do you know why there is an inclined line there? Bit of history on Galileo, and Adria, you cannot answer.
Okay, so if I cannot answer, then I have to ask the audience.
Yes.
What can be the reason for this? In the middle orbital plane, we have not all satellites in green. We have 2 that are not apparently not in the plane. What can explain that? Any volunteer?
There was a problem in the launch, no? And so they were in the wrong orbital slot.
Yes, that is correct. So there was a problem in the launch. They were put in a much lower orbit and very elliptical, and then over time they were put in an orbit that was as close as possible to, let's say, a usable orbit for receivers. And this is what is expressed here. So I'm not showing it there, but if you looked at the eccentricity of these orbits, you would see that unlike the others, which are in circular orbits, they are eccentric. So, for example, when you search for the satellite, the Doppler may be sometimes higher than expected, and there are other consequences. The orbit is not so easy to predict. So you have some issues with ephemerides and so on. And then at some point, it was decided that because some receivers had problems in tracking them, they were declared as not usable, and this is why they are in orange there. So we don't call them anymore wrong orbit, but we call it a different orbit, just to ensure that the satellites are not offended. Okay, so back to the presentation and the serious talk. If you want some information about Galileo satellite metadata, meaning the offset between the center of mass and the antenna phase center, many other information models that we use for the orbits and so on, they are in this address. So that was all about Galileo. I don't know if there is any, before we move forward, and in order to make this a bit more interactive, any question about Galileo that you want to ask?
Not for the moment. Just let me complement the information about these 2 non-nominal satellites. They have been used also for scientific purposes. They have been used to test the relativity effects on those very stable Galileo clocks. There are very interesting studies performed by different universities about how the redshift, how the gravitational effects those very stable atomic clocks. So don't think that they are unused. They are used by the different institutions and for different purposes. So they are not space junk. Is that
Yes.
right, Ignacio?
That's absolutely correct. And yeah, I remember a couple of papers written on the measure of the redshift effect of the gravitational redshift effect uh, by these two satellites that was much more accurate than any other measure of these taken in the past. So this is an example of a very good idea for a scientific use of these satellites. I can also say that the satellites are being connected to ground regularly as any other satellite in Galileo. And my other task is to work on Galileo authentication. So in particular, we have done OSNMA, the message authentication mechanism, and it is being transmitted by these satellites at the moment. So they are, to many effects, they are usable. And even if they are declared as, let's say, not usable, this is the, let's say, the official naming, but at the end, the users, as we know, and the receiver manufacturers, they are very smart, and sometimes they use things that are not meant to, and these satellites are can be an example. So they are there, and they can be useful. They can be added to the cost. I mean, to the satellite mix in the position, and then they can have other uses.
Mm-hmm. Okay.
Very good. So I hope you have discussed a bit the relativistic impact in Galileo satellites, because it's one of the most interesting, or at least a very interesting effect, or let's say a very interesting physical effect in satellite navigation. The fact that we have to take into account relativity, the fact that we have to take into account when building the clock on Earth, and also every time we calculate the clock, for example, as Adrian knows for sure, you have to take into account the relativistic effect if the orbit is not circular, even
Yeah.
with a small eccentricity.
Yes, yes. We saw these effects yesterday on Jaume. Professor Sanz was mentioning them in the yesterday lecture. So everything is controlled now.
Yes. Okay. Very good. Good. So talking about relativity and its impact in accuracy, let's talk about GNSS accuracy. So this part of the presentation is just to give a bit of the context of how accuracy has evolved over history. And we start in the 90s when GPS was declared operational. And at that point, as you probably know also, the GPS transmitted a signal whose purpose was to facilitate the acquisition of the military signal that is encrypted. So as a military signal is encrypted, it varies all the time. It doesn't have a code that repeats all the time because it's encrypted precisely. So therefore, if you are not synchronized with this code, and we are talking about 30 years old receivers, then I'm sorry if you hear a noise, but there are some works in the office. I hope you don't hear it as high as I do. But at that time, you needed to synchronize. So the Americans, with a very good technical criterion, said, okay, let's define a signal that repeats itself all the time, that is encrypted, that is unencrypted, sorry, and then we do the acquisition in this signal. Let's make a signal that is easy to acquire, and then once we have acquired, we switch to the military signal. But we don't want to make it very precise, because otherwise it will be like the same of our military signal, or almost the same. So let's add an error artificially. This signal is called the L1CA signal. CA stands for course acquisition. And I hope you have heard about this signal during the course, because it's the signal that we all use all the time. But initially, it was meant to be just an aid for the military users with this selective availability that was adding this error. So our history about GNSS accuracy starts in the 90s with this around 100-meter error positioning. By the way, I'm dividing this table in systems that are standalone, meaning no aiding, either from Sky other than the GNSS, or augmented. We say it's either assisted or geo-assisted, and then using spreading code positioning or carrier phase positioning. So we start in this part of the table, and then the next is, okay, then the civil community realized that this error is the same or almost the same uh, for a station that is nearby. And therefore, if you know the position of a station, then you can transmit the corrections to a receiver that you don't know where it is, and therefore you can wipe off the selective availability error. And this was the origin of DGPS, differential GPS. So with this, you could get a position in the order of a meter, something like that. Not only you correct the SA, but you correct also the ionotropo. So therefore, you can get a pretty decent accuracy for the time. But we are in the category of differential positioning because we have an augmentation, because we need a ground information channel to transmit the corrections. Again, I'm probably repeating things you know, but I hope repetition helps also you to get the big picture. And then also in the 90s, starting a bit early in the 80s, as soon as the GNSS signals were there, people started to use them for applications that required positioning, in particular surveying applications. So they started with static positioning. So you need to measure the position of a fixed point on Earth for surveying, and then you do it. You start to do it in post-processing. So you take measurements, you take the carrier. I mean, you take the whole signal and you use the carrier phase that provides this higher accuracy. We'll talk about that later. And then you take measures for a while, static, and then you post-process them, and then you get a pretty decent accuracy. And these techniques have improved over time and have led to what we know today as RTK, which is just the, so to say, the opposite of what I just said. Instead of static, it's kinematic, so you can move around while you are calculating your position. And instead of post-processing, it's real time, and this is what leads to RTK. But again, you need a base station some kilometers away. Otherwise, you cannot do RTK. We go to the 2000s now, we go to the other side of the table, and GPS realizes that because of differential GPS and other reasons, the selective availability is not very useful. Europe, for example, is building EGNOS, which is also correcting the SA. Even in the US, because we see the US as a block from Europe sometimes. Maybe, I mean, I don't know if this applies to Brazil, but at least in Europe, it looks like a monolith. But when you work with them, you realize that there are different views, as there should be, between different departments, different people, and so on. So therefore, they realized at some point, the DoD realized that the selective availability was not so useful, and therefore they switched it off. And this is what happened when they switched it off. On the 2nd of May 2000, you suddenly remove all these errors and you get to the level of accuracy that we more or less have nowadays, in the order of a few meters. In parallel, the US first, and then other regions develop SBAS, satellite-based augmentation systems. What you do with SBAS is you have a network of stations in a region, let's say the US or Europe, in the case of EGNOS, the European SBAS, and then you monitor the GPS signals, and then you correct any big errors like clock runoffs or wrong ephemerides that can affect the users by a big, let's say, amount of error. And then you also correct the ionosphere. And then by having this extra accuracy, you not only provide the accuracy, but you provide a bound to the accuracy, achieving integrity. So this is what allows that we use GPS or GNSS for precision landing approaches, thanks to SBAS. Otherwise, without SBAS, we couldn't use GPS with guarantees and do a precision landing down to 300 or 200 feet because you don't know if the satellite is telling the truth, so to say, or not. But thanks to SBAS, within 6 seconds, you know, so you can do the approach. Then in the 2010s, we have a new GNSS. So we start improving the accuracy because we have more satellites. So we dilute less the precision, so lower DOP. We have better signals, broader bandwidth, and so on. So improvement in accuracy. And then in the 2010s, we start to have precise point positioning. And this means we have absolute positioning, but with some assistance that provides us some accurate corrections that allow us to use the carrier face positioning, even if we don't have a station nearby. Because of the long convergence times of PPP, some commercial providers develop PPP RTK, which is you use RTK at the beginning, and then you can switch to PPP, simplifying a little bit. And then this is where we are now, which is, let's say, the best scenario, in the sense that it's standalone and it is very accurate. And this is what we are trying to do with Galileo for the first time. So standalone, global, absolute positioning with PPP, with an accuracy in the order of the decimeter, let's say, for the moment. I'm going to check the time because I don't want to be too late. We had sorry, we had 1 hour for this talk, right?
Have 1 hour, but take your time. It's
Okay.
better to have a late lunch than you to hurry in the presentation. No worries.
Okay. Okay, thank you. I think it will be less, so we'll have a bit of time for Q&A, but I I think it would be quite unfair if we have to, make people wait for the lunch if they are hungry. Anyway, we move to the next block without further ado. This is probably the more technical, so I hope I explain everything right. Otherwise, Adria, please interrupt or correct, and I hope there are no typos. Well, I start with a little bit of a joke. I hope no one is offended, but we have I mean, when we talk about carrier space accuracy, it looks like it's very easy because we used to say, okay, it's a centimeter level accuracy measurement. So the translation to a centimeter level accuracy in the position is very it's straightforward. It is not at all. So there are many things on the way: satellite orbit errors, satellite clock, and receiver clock. Okay, receiver clock is part of our navigation solution, but you have to correct it if you use different frequencies. You have biases from the equipment that you use that are different per frequency. You have to correct. You have the ionosphere that you have to estimate very precisely or remove at a price. You have the troposphere that you may need to estimate, and you have the integer ambiguity. And I put the question mark here because sometimes the integer nature is broken if you, for example, want to correct the ionosphere or depending on how you compute it. So not easy, and this is what we are going to talk about now. So we are my idea here, and Adria and everyone, please tell me if you have already gone through this, is just to give an example end to end of how a user can, let's say, go from standard few meter positioning to centimeter positioning by measurement combinations. But you probably have seen that. You probably have seen RTK, double difference, single difference. I think so, right?
We have only seen the PPP formulation, but not the RTK. So there is no problem to go slowly through these equations.
Okay, very good. Very good. So in fact, I didn't talk. I mean, I will talk about PPP when I talk about Galileo has, but I didn't enter in too much detail in the equations for PPP because RTK, I mean, is somehow easier to explain. Anyway, we start with the pseudo range equation that I hope you know by now. I hope you don't mind the formulation I use, which is the simplest. No sub-indices or super indices. You have just the pseudo range measurement, and then you have the range, which is what you want to measure, distance between the satellite and the receiver. But you have the ionospheric delay, you have the tropospheric delay, and then you have the biases from the receiver that I'm calling B here, and the satellite that I'm calling DT, multiplied by speed of light. And then you have an additional error that I am including there. I am putting there where I'm putting multipath and noise. Multipath I think you know what it is. Noise is generally what encompasses the thermal noise in the receiver and other radiations, sampling, quantization, filtering, and so on. So this is a standard pseudo-range equation. And what we have here is that, well, we leave this one aside for a moment. The satellite clock is giving an error that depends on how accurate the constellation is. So as you may know by now, in the navigation message, we are providing a clock correction. So we are telling the user how much off is the clock of each satellite, which is in practice better than correcting the actual oscillator. So we leave the oscillator oscillate, and then we tell the information of, okay, this oscillator is off by a few meters. And then we have the ionosphere that can go from a few meters to tens of meters, I would say, if you don't correct it. So we haven't applied any corrections yet. Same for the troposphere, so it can be as high as the ionosphere. And then noise is in the order of a meter or so, depending on the signal. Multipath is also very variable, can be 1 to a few meters to even hundreds of meters if you have no line of sight multipath. So a lot of errors. The first thing you do in a normal receiver, even without talking about carrier phase, is you correct the pseudo range. So you correct the ionosphere with the ionospheric model that you get from navigation message, Klobuchar in the case of GPS, Nequik in the case of Galileo. You correct the troposphere normally with a local model. So you estimate the dry delay, which is the biggest contribution, then the wet delay, which depends on how wet the troposphere is, or how, I mean, if it's raining or not, these kind of things doesn't contribute that much. So at the end, with the local model, you get an error of a few decimeters in the troposphere, and then in the ionosphere, 1 to a few decimeters. You normally correct like 50% of the error in nominal conditions, staying at the meter level. Multipath and noise, we haven't done anything. And then satellite orbit and clock, we haven't done anything. I talked about satellite orbit here. One could say, okay, why satellite orbit? Where does it appear? It doesn't appear in the pseudo range equation, but when you solve the system, you have to take into account for the estimation of the pseudo range. So rho hat, and therefore it gets into your position. So you have to have accurate orbits as well. And then we look at the carrier phase measurement equation, which is very similar to the pseudo range. As you know, pseudo range comes from the DLL, the delay log loop, which is measuring the delay of the signal, and the carrier phase measurement comes from the PLL, the phase lock loop. So you are also measuring the carrier phase of the signal in order to demodulate the bits, and also you get the carrier phase measurement. But the carrier phase measurement is very accurate, but it includes an ambiguity, the famous ambiguity, the so-called integer ambiguity, which is a number of cycles, that you don't know between the satellite and the receiver. In addition, the ionospheric error is subtracted. And the best advantage is that the error in the carrier phase is much slower. So before, here we were talking about errors in the order of a meter. Here we are talking about 100 times less, so centimeter level. So this is the main advantage of using carrier phase. And this one, the integral ambiguity, is the main disadvantage. So our objective is to reduce all errors as much as possible so we can solve the carrier phase ambiguity, meaning that if we have a measurement that is so accurate that we know everything so well that we can determine n, then we can have a position in the centimeter level. So what are the options that we have? The options that we have is we can reduce all of these contributions to something in the centimeter level, and then we can solve the ambiguities, or we can do linear combinations of the measurements that make some of these errors disappear because they are common to two measurements. And actually, high accuracy techniques try to benefit from both. In PPP, for example, as we don't have in PPP, we can do differencing, but only between satellites because we are standalone, you remember. We have just one point. So one of the pieces is the point that we are trying to solve, but we have nothing around. And so therefore, we need accurate corrections because with measurement combinations, it's not enough. And in RTK, because we have a reference receiver that we know where it is, we can benefit more from measurement linear combinations. So now let's see an example. So let's look at real-time kinematics. So we assume that we want to get the position of the tractor, our user, U, and we have a reference station which is around 10 kilometers away that we know very precisely the position, and we can synchronize the measurements between these two. So what is the, let's say, yeah, well, I say it already. What is the first measurement combination that you would do? That is what we call single difference. Anyone can tell?
Does anyone like to take this question? We have not seen the single difference formulation of RTK, but is there any brave here on the room?
Okay, forget about the term, because single difference, I mean, sometimes we use a lot of terms that are blurring the concepts, but at the end, the concept is very similar. So very similar, very easy to understand. So yeah, someone that wants to say, I have two pseudo ranges from the U and from R. What can I do with them in a smart in a smart way?
So,
I mean, we talked about it. Yeah.
So the question from Ignacio is, what can we do with two pseudo ranges, one from the user and one from the receiver, to build to improve the positioning? Any thoughts on that? Everyone is so shy here at the room. So, sorry.
I didn't understand the question. I repeat, please.
What can you do with the measurements?
I think that you can use the combinations with pseudo range and phase and apply, for example, IO3 or other types. You can use two types of station, and that's it. I think that's it.
Here, the proposal is to build a iono-free combination. Everyone hates the ionosphere as much as possible. So,
yeah. It depends what you hate most. So for the moment, so you can see the screen, no? Still.
Okay. Yeah. We can see your screen.
Okay, but you can see my point. Okay, but now you can see that. Okay, so yeah, I mean, we can remove the iono, so that is correct. Not by the iono free, but let's see it differently. If I have the two pseudo ranges that follow this equation, what are the errors that I can get rid of if I have my receiver and the reference station that is 10 kilometers away? Out of this error, or let's say out of this, and I didn't talk about the bias here because you will calculate it later, but what are the ones that I can get rid of in my user receiver? That's a more concrete question. I can get rid of because they are common to both measurements. So I subtract one by the other, and then they just disappear magically. Well, I think we can move forward. So the errors that disappear are the ionosphere, because 10 kilometers is more or less the same. Okay, Adrià may object to that, but I think most of the time you can, I mean, leaving aside scintillation and other effects, I don't know in Brazil, the iono activity is higher probably. So, but in general, we assume that it's around the same, so we can remove it. The troposphere as well. If you are in distances like this. And then the other component that you can remove is the satellite orbital error. That again doesn't appear here, but we'll remove it. And also the clock offset in the satellite. Okay. So by subtracting, I am now doing the single difference of the carrier phase, but at the end it's the same. By subtracting one by the other, so U minus R, I subtract these components from this, or let's say, yeah, this from this, and then these are the same. So IU is the same as IR, more or less, TU is the same as TR, DT is exactly the same, and therefore they just go. And then I end up with an equation that has less error. So I am closer to my objective. I have a slightly more complex ranging, which is just the baseline. This is what I'm measuring now instead of the distance from the satellite, but I have less errors. And another price I have to pay is that I increase my noise, because I have, instead of one noise distribution, I have two. And assuming Gaussianity zero mean, you apply a factor of square root of 2. Okay. Next step is to get rid of the receiver biases, because if you remember here we have this term, so BUR is the bias. Now, before I mean, if I have only one receiver, I have one bias. If I have two biases. So I want to get rid of them. So what do? I do again the difference between the between what I get from one satellite and from another. So remember, we come from the single difference, but we do another difference now. This is what we call the double difference. Again, a term that appears very often in SatNav. It's not more than doing a single difference twice. And now what I do is I subtract the measurements that I had for U and R from my single difference from one satellite. Now I put the super index here. I didn't put it before for simplicity, from the other. And what I do is, because the measurement UR had this common UR bias, but it's common to phi k UR, so phi super k sub UR and phi super L sub UR, it's the same, so therefore it goes. And then I end up with just something that depends on the range, which is what I want. Now it's a bit more complicated because it's the baseline. So yeah, from K without entering in the detail, it's a bit more complicated conceptually, but it's the same when you solve it. And then you have also an n term that is a linear combination of 4 terms for U, for L, and for K, and for so U, R, K, and L. Sorry for the explanation if it's not clear enough. And then you increase a little bit the error in the carrier phase noise. Before we had square of 2, now we have square of 2 again, so we have 2. But the advantage is that now we have only one term that we don't want, which is the n. And then to finish with the explanation, how can you remove the n? Well, you can do several things, but I will explain the easiest to understand, which is what some call triple differences, which is you just wait, and if the carrier phase measurement is locked, so you don't have cycle slips, so your carrier phase measurement is continuous, then the n term is continuous for all of the carrier phases here, from this satellite to here, this satellite to here, and the other two. If this is continuous in time, then this term n is continuous or doesn't change between T1 and T2. So therefore, if you wait a little bit, or a little or a bit more, then you can generate some equations that are that occur at different times, and therefore you subtract them, doing the same process as before, and what you end up is with one measurement that is composed of the linear combination of several measurements, several satellites, 2 receivers, and 2 instances in time. But that does not depend on any error contribution apart from my very small, as we said, carrier phase noise. So this is exactly what we wanted. So we managed by linear combinations to go from measurements that contain a lot of errors to a measurement that is only depending on the carrier phase error that, as we said, is very small. So this is very good. Now, I would ask, and this will be the final question of the block, what could be the disadvantage of that in relation to solving the system of equations? So if you have talked about the rank of the matrix and the illusion of precision and all that.
Okay, can anyone take this question? So the question is, what is the problem with this formulation of having built the double difference measurements? You can answer.
The correlated measurements maybe one of the problem.
Yes, understanding correlation as let's say geometrical correlation, that is correct. So the problem is that if they are very close in time, then the ranges will be very similar. So what happens is that when you create your design matrix, the matrix that will allow you to solve your system of equations, then there will be some rows that will be almost the same. So if you may remember from linear algebra courses, that if you have, I mean, your rank is reduced if you have two rows that are the same. So in this case, they will not be exactly the same, but they will be almost the same. So what that means is that when you solve your system, you have in some components, you have a lot of uncertainty, and therefore this degrades your solution. And therefore, you have to wait a lot in order to have what we call geometric diversity. So this is the main disadvantage of this process that I use to explain, how to get rid of errors through linear combinations, because it's relatively easy to explain, but it's not optimal. So things that you can do is, well, the iono-free that apparently you are fond of. You can do also, I mean, you can play with combinations, so you kind of artificially maximize the the wavelength of a linear combination of the two signals in order to help solve the ambiguity. You can do the opposite with the narrow lane. So there are many techniques. I won't enter in the detail, but I suggest you get you check these two references, which by the way were written by the UPC group. I think Jaume is the main contributor here for the combination of measurements, and here for combinations of range and carrier phase. I think you already talked about that. So you can not only combine like measurements of carrier phase with carrier phase, but also carrier phase with range, for example. So the simplest thing is if you subtract one by the other, you get the iono, sorry, if you add one by the other, the iono should go because it adds in one case, pseudo range, and it subtracts in the other, carrier phase. So this is a simple thing you can do. And there are others. The Melbourne-Wubena combination is a very well-known one. And then there are techniques to resolve the ambiguities altogether. Lambda method is very well-known. I won't enter in the detail there, and I will move to PPP because we are lagging behind, and I haven't spoken yet about high accuracy service, which is what I was going to talk about. So these are the PPP equations. So I understood that you are already more familiar with this. One thing I wanted to highlight is, again, on the errors, this error from the code phase measurement or pseudo range is coming from the DLL. And this is a typical output of the DLL. I don't know if you talked about the correlators, early, late, the discriminator, what you get from there. But the thing is that you get an error that is much higher than the error you get from the carrier phase. So the carrier phase, you use the I and the Q, so the correlator with a replica, and then with a replica shifted 90 degrees, and then with the two, you kind of determine this very accurately. So this is, for example, a result from a real correlator, not very good, but yeah, you can see here that on time, that you cannot see here, you may have some, some noise according to this, which is what gets here. But in phase, the noise, so if you take this circle, for example, I mean, you can have a few degrees, but think that 90 degrees is 1/4 of a cycle. 1/4 is less than 5 centimeters. So we are talking about a very, very low error. So this is the important thing about the carrier phase. You can see it there. The thing is that now we cannot do combinations with the rover or the reference and the rover, the U and the R before, or user and reference, but you have to get the iono, the tropo, and the integer ambiguities. You have to find a way to find them. And the best is that you get as much information as possible from another source. So here you have the formulation for the iono-free. So one very simple ways to do the iono-free, and then you get rid of the first order of the iono, which is very good. The price to pay is that you multiply your code error by something higher than 2, between 2 and 4, or 3 point something, depending on the combination you do. So this is quite relevant, and it's not very good. And you make the n non-integer because you multiply by a non-integer number. So therefore, your n loses the integer property. Again, I won't talk about this in detail. You have the tropo for the tropo, you can have it corrected, or you can have the tropo calculated. The good thing about the troposphere is that if you estimate the delay at the zenith, then with a mapping function, you can map it to different slants or different elevations relatively easily and with reasonable accuracy. And then if you look at it from the other side, meaning that you get someone that provides you with very accurate orbits and clocks, like Galileo, then for this provision of very accurate orbits and clocks, the ODTS, the orbit determination and time synchronization module, needs to use very precise models for the orbital errors, including solar radiation pressure, antenna phase center of course. I mean, the thing is that you normally calculate the orbit for the center of mass, and then you transmit the signal from the antenna phase center, so you have to take into account these offsets, and also phase center variations, phase wind up, which is an effect that happens when you rotate the antenna 360 degrees, the rotation of the Earth. So, I mean, where is the Earth? How much it rotates? This is not constant. Where is the pole? What are the tides? So there are many effects you have to take into account in the ODTS. And then you need to provide the data. So you need a real-time monitoring and communication systems. And this is what we try to do with high accuracy service. So last slide before talking about high accuracy service, this is a typical state vector that you have when you do PPP, which can include the position, the velocity that helps to predict what is the next value of the state vector, the clock bias in ionophore, the zenith tropospheric delay, and then the ambiguity. So this is just an example. I mean, you can have different ones, slightly different, but this is an example of a state vector of a PPP solution. And then a typical way to solve PPP is through a Kalman filter. So I think Jaume was talking about Kalman filters before when I joined for a few seconds to check that everything worked. So it's very used in SatNav, very used outside of SatNav, and it is very effective if you want to converge to a high accuracy PPP solution. As we said before, the problem is converging to solving the ambiguities. Yeah, I think I will switch to high accuracy service. Any questions so far? I think yeah, it's a bit late, but I will try to cover it.
We have a quick question here at the room. So
Yes.
but make it quick, that we are getting late.
If I take the RTK or PPP, I can apply the test hypothesis method to increase the quality of this model. I talk about that if you can test the residual errors when in the adjustment to remove the satellites that spoil the position. It's possible for these two methods or not, or it's not necessary in these types.
Well, it's necessary, it's possible, first of all, and it's almost necessary. So one thing to bear in mind is when you select when you do the differences between satellites, normally what you do is you take like a reference satellite and then you do the difference with that reference satellite. This one is normally the one at the highest elevation because it's the supposedly best one. So you take into account the geometry and other factors that you have to select the satellites. You can look at the residuals, but you can look also at the C over N0. You can look at the elevation. You can have a weighting matrix, measurement covariance matrix. I mean, these things are at the core of high accuracy. So it's quite a relevant comment. Thanks for mentioning it because I didn't. But yeah, definitely you take into account the different quality of different measurements, and you take out outliers. And I will talk about outliers a little bit on high accuracy in a few slides. Because it's a bit late, I would ask Adria, if you don't mind, that we finish like 10 minutes later. I hope it's not a big deal because I think this is the list I would need to cover the hash.
Sure. There is no problem to end a little bit late. So take your time.
I tried, but finally the RTK part took a bit longer than I expected. Sorry for that. Anyway, so now let's talk about Galileo High Accuracy Service, or HAS. So HAS is a new service of Galileo that provides accurate orbits, clocks, code biases, and phase biases for Galileo and GPS, and for these navigation, let's say, messages and these frequencies. We didn't talk about code and phase biases. I mean, we have talked about orbits and clocks for sure. Codes and phase biases appear when you use different frequencies, and there are some effects apart from the IONO that is frequency dispersive. There are some effects, sorry, that in the equipment of the satellite and the receiver that are different at different frequencies. So this is what we call biases, and we estimate them separately for the code and for the carrier phase. So this is why we have code and phase biases, and then we apply them for different frequencies depending on the frequency combination. So we get this very precise orbits and clocks, and then we have biases for any frequencies that we transmit in Galileo, and also some frequencies in GPS. We expect to provide an IONO correction service in Europe. I think Adria is familiar with that, at least, and but this is still in the making. For the moment, we have no ionospheric corrections. We talked before about iono-free. It prevents solving the integer ambiguity, so it's better that you have good iono correction, so you don't have to do the iono-free, or you do the iono-free, but you use the iono correction and you kind of put it somehow in a smart way, and then you improve your performance. We transmit the message, the hash message, through the satellites in the E06B, and also through an RTCM-like format. RTCM is a standard format for transmitting corrections. We transmit all the data that we want in a few seconds, and then we also have a kind of mask and the flagging system that allows to take satellites out if necessary, as in relation to the previous question. So this is a scheme of the hash architecture, and here you can see a bit in more detail some information. Well, the main information on the signal. It's transmitted by Galileo. Here I put it in context with other high accuracy transmitting services. QCSS, the Japanese one, is providing corrections regionally. You have SBAS, that is not a high accuracy service, but it's being considered for using high accuracy. And you have commercial services, for example. They are also in the L band. They have normally broader bandwidth than us. We have 448 BPS per connected satellite. And these are the features of the signal. Due to lack of time, I won't enter in the detail. You can look at the ICD, the GSE website, program documents. You can find all the information. Oops. So here you see the ground infrastructure, which probably reminds you to the slide with the ground infrastructure that I showed before, because it's the same in ground infrastructure. So we are not adding any monitoring station more for hash than what we have for the normal ephemerides. We have only the HADG, or high accuracy data generator, located in Torrejón, Spain, in the GNSS service center, within the GNSS service center premises, but the rest is the same. So we have to do our best with very few stations. So just for reference, usual PPP services have in the order of 100 stations, something like that. We have 14. We have 2 stations per site. So in fact, one could say we have 28, but it's only 14. So this is the signal in space interface control document message structure. So again, I won't enter in the detail, but I will just say that we have 448 bits per transmitting satellite. And these are divided into a header of the message, and then the message itself. The message contains this information. So 3-dimensional orbit corrections, radial, in-track, and cross-track, clock correction, and then biases for the different frequencies. Just to say, the clock correction goes to in relation to the navigation message, and the navigation message of both GPS, LNAV, and Galileo INAV is related to the iono-free combination. So therefore, this delta clock correction is not related to a physical signal, but to the iono-free combination of 2 signals. And then if you want to use separate and combine the signals, you have to apply the code biases and phase biases. One thing to say here is that we are very happy with the way that we have developed this, because we managed to get the information through, so all the orbits, clocks, and biases, in a few seconds, like 6, 7, 8 seconds in good conditions. So think that the normal navigation message in the current iNav takes about 30 seconds. So with the hash, we take about 6 to 7 seconds, something like that. So one thing that we have to consider is that we have to relate the orbit and clock information. I'm sorry if you are hearing a noise. Sorry for that, but as I said before, there are some works going on intermittently. So we have to relate the corrections to the satellite. So we provide corrections to the navigation message, and every batch of satellite information of ephemerides and clocks includes what we call IOD, issue of data. So we relate through the IOD the message or the set of data to which we have to apply the corrections. And now we go with the results. So here is an example, a relatively recent example from July 2022. This is mainly the slide I proposed to Eric Chatre, the head of services and evolutions, to present at ION GNSS. So I'm anticipating that. But anyway, here you can see some results of HAS. Here you can see some results of HAS in July with some convergence. So you can see here the convergence time, not much here. And then you can see that after things are stabilized and the accuracy is in the order of the decimeter. These are solutions with GPS and Galileo together. And we are using the ion of free combination. We are using float ambiguity, so we are not trying to solve the integer ambiguities. And we have a static open sky environment. So these are results in the validation from the validation phase, but as you can see, the performance is very high already. We foresee the initial service declaration by the end of this year. Another important feature that I said before of high accuracy service is isolating and removing satellites that are faulty. So in this case, this is a real event from 2021 of a Galileo satellite with a clock runoff and went up to more than that, more than 100 meters. And by following the hash corrections that were transmitting the signal in space at the time, the corrections followed the trend of the satellite clock and then took the clock out of the mask. So if you had used hash, you wouldn't have experienced this, so the error in the position due to this satellite runoff. It's another feature. It was not intended like that. There is no integrity provision, not at all, but it's an interesting feature that can be used for that purpose. Now, looking at the applications, and I'm almost finished, I won't enter into the detail. There is a document called Hash Information Note that talks about how high accuracy service can contribute to many different applications, including professional sector, also including mass market. Autonomous vehicles is like the main application that everyone is looking at. Smartphones, it's difficult to do high accuracy because of the antennas and other effects, but they are progressing a lot. And there are also safety of life applications that can benefit from HAS. As I said, we provide no integrity, no safety of life warranty, but nevertheless, HAS can be an interesting contributor. And now to mention a bit of an exotic application, there is a recent paper from our colleagues from DLR of using high accuracy service with Sentinel 6A positioning. This is a satellite, a meteo satellite from the Copernicus or Earth observation from the Copernicus constellation in Leo orbit. And they applied hash corrections to the GPS and Galileo messages and compared the results with IGS results, with the ultra rapid in particular, which are still not real time. So you see that with some degradation with respect to IGS, the results are pretty decent. So if you look at the hash solution with GPS and Galileo, and I recall this is real time, no ground assistance, so the satellite can compute this in real time without any link to the ground, you can already get to the to an average below the decimeter level total error. You have the reference if you want to see more details. And with that, I finish my presentation. So I thank you very much. I apologize for the delay, and I welcome any questions that you may have. I hope you find it interesting, and I wish you the best also for the rest of the course. Any questions then?
Hi, thanks a lot, Ignacio, for this very interesting talk. And you are getting the forms of a university professor, always talking and talking and talking, which was very, very nice. I have myself one question before I open the floor for questions. What is the status of the phase biases? Are those being computed also now in the current phase of the Galileo hash? Or what is the plan with the phase biases to enable ambiguity resolution?
That's a very good question, Adria. They are computed now. They are being broadcast now, as far as I know. So wherever you are now, where are you in Brazil, by the way? In which?
In Fortaleza, in the north east part of Brazil.
Okay, so that's not a particularly bad area for hash, because we have the Kuru station and we have some stations. So I think right there and right now you could receive the phase biases. However, their values and the algorithm is under experimentation. We have some corrections going on with the ground stations, because there are some tracking issues with the carrier phase in some stations, and this is affecting the phase bias computation. It's very challenging with so few stations. So phase biases are being transmitted. Our intention is that they are part of the initial service, but while for the other parts, code biases and clocks and orbits, we can confirm that they are in the initial service, phase biases is really the remaining point that is now taking most of our efforts. So your question was quite spot on, Adrian.
Mm-hmm. Okay, thank you very much. So I will open now the questions from the audience. Is there any question here? Yeah, we have one question.
How accurate are the opts and the clocks computed by the Galileo hash?
That's also a good question. I cannot answer by heart, but if you give me a second, I can give you the values. So from the latest tests that we have, we see well, I can give you the values in what we call 1D RMS, which is quite a standard. The Galileo orbits are computed with 5 centimeters 1D RMS, and GPS with around 6-7 centimeters 1D RMS, and the clocks with between 0.15 and 0.26 nanoseconds standard deviation, 1 sigma. So these are the values that we get that we are getting now from the last analysis that we have. They are just reference, but we believe it's a representative reference. And there is one paper that is referred in the presentation that presents with a bit more detail what I just said.
Okay. Is there any website like with EGNOS or with from SSSP or any other company in which it's can we see the performance in real time, or not yet for Galileo hash?
That's a very good suggestion, but at the moment there is no such website as far as I know. Take into account that this information I'm presenting is very fresh, and the signal in space started broadcast with the operational ODTS just by end of July. So we are really at the beginning of this. So we haven't got this initiative internally, or we haven't seen anyone that is taking the initiative. By the way, Adria and your group, if you are willing to take that initiative, let me know, and it will be welcome for sure.
We are for the Iono part. We are doing our own experimentation and the computation for the Iono for hash. So this is we have a real-time website in which is computing the ionospheric maps.
Okay, I that's very good.
Give you the details later on offline. Okay, so I don't know if there is any question from the chat, from the Google Meet. I don't know. I think we have also connected Jaume. I don't know if you want to ask something, Jaume, or we close it here.
Thank you, Adrian. Not now. Thanks a lot. It was a very interesting presentation. Thank you so much, Ignacio.
Thank you very much, Jaume. It's a pleasure to hear you and be part of this course, as I said. I see that you have a new student, no?
Yes. Yes. It's my granddaughter.
Wow. Congratulations.
Thank you.
The new generations. Okay, so we will close here the morning session. So now we proceed for lunch, and then we reconvene at 1:30. Okay, so thank you very much for attending this morning session.
Thank you very much, Adrià and Jaume. Thanks, everyone, and sorry for the little delay. And I wish you a good lunch and a good rest of the course.
Thank you. Thank you.
Thank you. Bye-bye.
Bye-bye.